So good afternoon, everybody. We continue our examination of the methodology for algorithm design. And just a quick recap. We have used a method by which we will create an initial solution, which is a recursive definition, for which we'll give an inductive proof of correctness and analyze it using recurrence equations. And solutions to recurrence equations, the asymptotic notations, all of that has been discussed. Then we will explore the possibilities, and there among the two things that we saw was how do you optimize the split, and we saw the max and max problem, the max and min problem, and the max and second max problem. Then we moved over to the Fibonacci series, and where we looked and encountered identical subproblems. So these were the two critical things that we have seen till now. We also, as a byproduct, we also looked at this concept of data structures, about how to remember things in such a way that they can be more effectively used in the future. More importantly, we wanted to also look at analysis in a more comprehensive manner. And for that, we developed the whole concept of recurrence equations, recurrence relations, and the asymptotic notation. Having done the Fibonacci numbers the last day, we came to the conclusion that in general, the problem is like this, that we have Fn equal to some Rn, which is the base condition, Rn for which the base condition, so this is the base condition, this is the base condition, so let me use a different color. Sorry. So this Cn is the base condition, and Rn is the solution for the base condition, and it does recursively decomposes it into two parts. If Cn is false, that is the recursive condition, and this is the recomposition function. We will use these terms again and again as we proceed. Here it is addition. In general, it could be something else. So Cn is the base. We currently assume that G, H, R are non-recursive deterministic functions. So for the time being, we identified that we need to have an efficient method to evaluate Fn. And the three important issues for evaluation of Fn is that obviously we don't want to solve identical subproblems again and again. We also identified that we can reach cyclic conditions, that is Fn through Gn, Hn, Gn, Hn, etc. calls Fn again before solving it. So if it calls it again, then we have to flag the dependencies. And we want to also, because here we don't know how many n's, which n's will be required to compute Fn for a given n. So what will we declare? How much memory will we declare? So these are the three issues that we shall address for some time today before we move on to something else. Anybody has a point up to this part? Is it clear to everybody? Arya? Arya, Rajendra?
Yes, sir. Yes, sir.
Okay. So our way of writing this, by the way, in the course webpage, you have all these slides there, but whatever we do in the class, I will update the slides which I write in the class along with the class videos in the Teams. So you will have whatever I'm writing now, you will have that as well in the Teams, in addition to what is there in the coursework. So our basic evaluation function is this, which says that if Cn is true, return Rn. Otherwise, compute x equal to Gn, y equal to Hn, z equal to f of x plus f of y, and return z. Is this clear to everybody? Akshay Mandal?
Yes, sir.
Good. So now, what are our challenges? Our challenges are how to detect loops, how to optimize memory, and obviously how to remember. So we will use our traditional method where we will use an array f. Now, how much of f to declare, etc., we will come to. And we'll declare an array done. Again, how much of done to declare, I don't know. What values of n will be required? If we know, obviously we can declare upfront. If we don't, we have nothing. Now, previously, pay very careful attention. We were writing done I equal to 0 if the value was not obtained, and done I equal to 1 if the value is obtained. But now, because of that cycle, we use three values. One is if it has not yet been called, I write 0. If it has been called, but the function has just been called, then I write 1. And if the value is computed, then I write 2. Can anybody tell me what is the purpose of having three values now?
So to detect cyclic dependencies.
Right. When will you detect a cyclic dependency?
If it shows 1.
It is called again.
Yeah. So what will happen to done if it is called again?
It will be 2, sir.
It will become 1.
2 or 1 or 0?
1,
It will be 1.
1. Whosoever said 2, are you sure it is 1?
Yes, sir. Now I get it.
So now here is the base condition. This part is clear. If the basis is true, done n is equal to 2, fn is equal to rn, return fn. Now that f array, how to declare, will come to. That is a question. The second part is, as somebody just identified, if done is 1, I have detected a cycle. Gaurav Jha, are you okay with this?
Yes, sir.
The third is if done is 2, then what do I do? If done is 2, that means what has happened?
We return the value.
Value is already.
That means it is already computed. So so it is an identically solved problem which has been solved before. Now, if none of these conditions hold, which are my conditions, then I set done equal to 1. I compute x, I compute y, I compute z, I compute the value of fn, and I will set done now equal to how much?
2.
2. And I will return. Now, we have not yet memoized. This is the value of Gn and Hn. We could have done that. What will happen if Gn and Hn are also recursive definitions and they also call Fn, or they call each other, all these, you think about it. So anybody has a doubt that now we have been able to correctly detect loops and we are solving an identical subproblem only once. Is this okay with everybody? What are the pitfalls remaining? That if the function is poorly defined, that it goes on infinitely, even though there is no cycle, then obviously we have nothing to do. Anybody else has any point of view here? Mihir Raj, are you there? Naman Jajani, are you there?
Yes, sir.
It's clear.
Yes, sir.
But I would request all of you to think that if G and H and R are also very complicated functions, then what to do? That you think. Now our main problem lies in what to declare F and done. So what did we mention in the last day about F and done? It has to be declared.
We'll declare it dynamically.
Dynamically. So I will require dynamic declaration of F and done. So when I have to declare it dynamically, F is also a set. Done is also a set. What will be my operations in this set? What is my first operation in this set? This dynamically, when I declare it dynamically, what will be my first operation?
The values are set to 0.
No, all that is so you have nothing. You start with nothing, isn't it? You start with nothing. Initially in your algorithm, your F is a null set, done is a null set. Nothing is done except for basis conditions. So F is a null set, done is a null set. What are my operations on F and done? What are my operations? Nancy? Nancy, are you there?
Yes, sir.
What operation? First operation is?
We check if the value exists.
Whether n is there in F.
Yes, sir.
So find F. If it is there, you can retrieve the value, isn't it?
Yes, sir.
Otherwise, what will you do?
Save the value. Compute and save the value.
Insert a value, isn't it? You will insert in F for the location n a value z. Is that clear? Piyush, Jangit, is it clear?
Yes, sir.
So I will insert. That means if the find says that it does not exist and I have to set the value of done or I have to set the value. So either I have to insert and set the value. So I will have to, this insert will also require creation. It will if find exists, I will have to get the value. If find does not exist, I will have to assign the value. So when will I create a new element or insert a new element? In this algorithm, when will I create a new element? When will I check if it exists or not?
When the function is called.
Right here. Just before done, I have to check. Nah? I have to initialize the value of f. I have to initialize the value of done. So before writing done n equal to 1, I have to check whether it exists. Before assigning done n equal to 2, before checking if done n is equal to 1, I have to check whether it exists. So now dynamically I will create elements which are happening and this will grow. So these two sets form my new what? New data structures, isn't it? Pooja Sharma.
Yes, sir.
So what will these data structures look like among the data structures that you have studied? How will you implement these two data structures? By Pratik Rakesh Singh. Pratyush Tiwari. Pratyush Tiwari, are you there? Ritam Talukdar.
Yes, sir. I am so thinking, sir.
So we have to implement a set data structure where we have to create a new element of that set. We have to find whether it is there. If it is there, we have to get the value. If it is not there, we have to create a new value and insert it into the set, etc., etc., etc. And we will see that such sets are form part of data structures that we design. We'll come to all these. So now we move on to another new problem. We move on to a new problem. Have you ever wondered your coins? What are our denominations in our coins and our rupee notes? What are our current coin denominations or the rupee note denominations? Can anybody tell me?
1, 2, 5, 10, 50, 100.
So we have got 1 rupee note or coin. We have got 2. We have got 5. We have got 10. Then
20,
20. Then
50,
50. Then
100,
100. Then
200,
200.
then
500,
500. Then
2000.
1000.
2000. 1000 is not there now. 2000. So now tell me, why did the government not create a rupee of denomination 3? Why did the government not create a rupee of denomination 7? Did it occur to you? Why was that not? Why didn't that happen?
So possibly because with the given denominations, we can have all possible combinations.
Yeah, we could have created these combinations using prime numbers also. Using prime numbers, you can create any number, na? Yes or no?
Yes, sir. Then
Yes, sir.
maybe it
Sir,
becomes
this is the
difficult to
minimum
calculate.
point distribution. Like for a given amount, this and these in denominations can be the minimum.
Right. So if you have plentiful of each denomination and you are asked to make a denomination final value of y, then what would be your algorithm? If y is 573, then what would you do?
You take the maximum value, maximum possible denomination, and
So first you take 500, then
Then 50 or 20
50,
or 2
then
and a 1.
2, 1. And does this give you the minimum number of nodes by which you can get 573?
Yes, sir.
Good. But is it true for every combination of such node denominations?
No, sir.
No, sir. So people must have thought and designed this problem. So we will look at this coin problem. So is the screen visible?
Yes. Yes.
So given a set C of n coins having denomination values C1, C2 to Cn and a desired final value of V, find the minimum number of coins to be chosen from C to get an exact value of B from the sum of the denominations of the chosen set. And what I have not written here is that you can choose one element only once. You can choose the coin Ci only once. Is the problem clear?
Yes, sir.
For example, if my coins are 8, 6, 5, 2, 1 and my desired value is 11, then there are two possible combinations 8, 3, 1. Sorry, 8, 2, 1 hoga na? 8, 2,
Yes,
1.
sir.
Yes, sir.
8, 2, 1 and 6, 5. Any other combination will work. Is there any other combination possible?
No, sir.
No. If I allow you to take any number of 8, any number of 6, any number of 5, any number of 2, any number of 1 denominations, then aren't there other solutions?
Yes, sir.
yes, sir. One.
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now, if I allow you to take a coins, one coin only once, and I give you an arbitrary choice of coins and a value V, is it possible that there is no such combination which will yield a value V?
Yes, sir.
Yes.
In this
So-
set of capital C, can you tell me which value V will not be possible?
So a
4.
trivial example would be 4.
4.
4.
4.
4.
3.
4 is not possible. Got it? So now my problem, my general problem, which we call the coin selection problem, and all these problems that we have been selecting are very typical because they will help you understand various classes of problems. So what is our methodology to solve problem when we have a new problem? What is our methodology? What is our first step in our methodology?
Base
So
case.
identify the answer to the simplest problems.
Recursive definition, है ना? We want a recursive definition to solve the problem. Isn't this what we are trying to do?
Yes, sir.
What is the reason for doing a recursive definition? Is that it will be an inductive proof of correctness. Complexity can be understood. And when you open up the recursion, what will you see? What is the first test when you open up the recursion? What are you going to see? Whether
Base case.
base case, so you have to write in the recursion. But when you open up the recursive condition, what are you going to observe?
Split.
Huh? I lost you.
So split.
Split. So we
All
will
possible
see.
subsets will, right?
No, but in general, what is our methodology? Itna bar we are repeating the methodology.
Recursive condition.
Not yet, not yet. Okay, let's do this problem. Let's do this problem. What did we look for in when we opened up the Fibonacci series?
If cycles exist.
And if cycles don't exist, then what else are we looking for?
If the loop terminates, means n exists.
I think you'll have missed out the most important part. Hana? Why do we want to look for identical subproblems? So that
we can remember them.
Reduce the number.
Memorize.
And once we remember them, efficient way to remember them creates what are called
Data structures.
Data structures.
Data structures. This will all give you an idea. All this, if you read from the book, what will happen is you will only learn what is told to you. But why did they do that? And if you get a new problem, what will you do? So let me take you through one recursive definition. The recursive definition is called coins. It has got 5 arguments. S is the set of coins selected till now. T is the remaining set of coins from which I have to obtain the value. X is the sum of the value in S. Z is the remaining value. And N is the number of coins chosen till now. Actually, all these are, so look at this. Which of them are necessary and which of these are derivable? Which is necessary to remember?
X and N.
S, T.
S and T are necessary.
No, and Z also.
Only T.
If I don't know how much I have to do, if I don't know how much is the remaining amount left or the total amount, then so S, T and Z. Is it clear that Z is important?
Yes, sir.
And what will I call it with? I will call it with S as null. T as my original C. The sum of elements in S as X as 0. The value to be obtained as V. And the number of coins selected till now is 0. Is everybody with me?
Yes, sir.
Yes, sir.
Yes, sir.
Ritik Prabhakar, are you there in class?
Yes, sir.
So now, what will be my basis conditions?
The base condition, sir.
What will be my base condition? First base condition is what?
Okay, the set of coins we selected is 0. We didn't select any coins.
But that is not my base. I have not yet selected any coins. Is not. See, recursion has got 2 parts. Base condition.
Okay, base condition is whenever our the desired value becomes 0 or less than 0.
So Z equal to 0, Z less than 0. This is one base condition. What else?
And if for a set of remaining coins,
X is equal to value.
T is null.
T is null.
No.
Nothing is left to be chosen. Anything else?
So then the desired value is simply one of the members in the coin set.
That we'll put it in the recursive part. So when Z is less than 0, then what are you going to return?
It's not possible.
Yeah, so you will return infinity. What will coins return? Coins will return what? What two things will coins return? Finally, in the base, it will return
Number of coins required.
S and N.
Yeah.
Yes.
It will return S and N. From there, you will get everything else. It will return, basically, it will return S. So here, you will return number of coins as infinity. When Z is 0, what will you return? If you call it on this, when Z is 0, what will you return?
sir, N.
S
N.
and N.
N.
S,
Very good.
S and
N. When T is 0, what will you return?
Sir, infinity coins.
No, T is 0. S contains something.
Yes.
Null.
No, it depends.
Like if X equal to value.
If
X equal to
Z
value.
is not equal to 0, then you will return infinity. But T is 0. But if Z is 0, then obviously you will return N. All right. If T is 0 and Z is not equal to 0, then you will return infinity. That means you still have something more to do, but you have nothing to select from. Rudra Jyoti Das, are you with me?
So for some reason I cannot see presentation for like throughout the class. I'm trying to fix that.
Sanskar Patni. Sanskar Patni. Shayan Laik.
Sir.
Have you understood or not?
Yes, sir.
So tell me why, if T is 0, why am I putting this condition?
Sir, if T is equal to 0, then we don't have to take any other coin to get a value 0, because without any coin we can get a value 0. So
If Z is not equal to 0, what is written there? Can you read this part?
remaining value is infinity.
So if Z is not 0 but T is 0, then what does it mean? Did you watch the pre-recorded video, or are you paying attention, or you're watching some cricket match or something like that? We are noting down all these things. There are a lot of marks in teacher's assessment. Shivam Dwivedi, are you there in class? Shivam Agarwal? Shivam Agarwal, are you there in the class? Interesting. I will stop taking class if people are like that. Just we'll remove all of you. I will suspend people from attending the class. If you are in the class, you don't respond, which means that you're not in the class. Navam Shingla, are you there?
Yes, sir.
So why did we put this condition? Z not equal to 0?
So because when the remaining set of coins from which we can select becomes 0, we cannot show that the desired remaining value desired is 0 or not. Or if it is not 0, then we have not any coins left.
Good. Very good.
Yeah.
So we've got our base condition in place. What will be our recursive condition? Anybody?
So from the set for all the coins present in T, like we select one by one.
Right. So we can recursively break it down into various options by selecting one coin at a time from T and adding it into S. Good. So that's what we write down now. So our algorithm returns PD, where P is the set of coins, D is the number of coins. Let S be S1 to Sn and T be T1 to Tm. We have already written if Z is equal to 0, return Sn. If Z is less than 0, return null infinity. And if Z is not equal to 0 and T is equal to 0, then return null infinity. So our base conditions are clear. Now my P min, because I will break it up, I will choose one coin at a time. I will break it up into sub problems. So from a problem P, from my original coin C, I will break it up into sub problems. As Ritam just mentioned, I will take one coin at a time, break it up into sub problems, and from the solutions of each one of them, which one will I take? From the solutions that is coming from each of these sub problems, which one will I take? Each of them will give me P1, T1, P2, T2.
Minimum.
Right. I will choose the minimum number of coins. So that is why I have initialized this like this. Is it clear to everybody? Manav Vardhan? Manav Vardhan.
Yes, sir.
So my recursive condition as per Ritam is for all elements 1 to M, M is the number of coins T1 to Tm. I will add it to Ti to S. I will delete Ti from S. So I have added to S. I have deleted and formed W. So I will now call it recursively on W, U. Now my X now becomes X plus Ti. Z becomes Z minus Ti and N becomes N plus 1. Mayank Beth, is it clear to you? Mohammad Ayman, is it clear to you? Lavinder Kaur?
Yes, sir.
And among all in the loop, I will check whenever I get some P dash D dash from a recursion, I will go on finding the minimum. And at the end of it, P min and min will be returned. Who has understood, please raise your hand. Those who have understood, please raise your hand.
Sir,
Yes.
as you have mentioned earlier that a value of 573 is obtained by first taking the maximum one like 500.
Here that will not happen in this case.
We can take the maximum value of coin for the
you look at this example. You look at this example, if I take 8 from 8, 6, 5 to 1 and v equal to 11, if I take 8, then I'm not going to get this solution. Hai na?
Yes, sir. Yes, sir.
Is your doubt cleared?
Yes, sir. Yes.
Okay. So now what happens? I have, this is my initial value in this example. This is my initial value. So I will choose 8. And if I choose 8, then this becomes 8. This is 8 is removed. X becomes 8. Remaining is 3. 1 coin is chosen. If I choose 6, then 6 is chosen. 8 is there. 5 to 1. And the chosen X is 6. Remaining is 5. 1 coin is chosen. If I choose 5, similarly, and so on and so forth. First level of recursion understood? Anybody has a doubt? Aparajay Singh? Aparajay Singh? Ankit Kumar Prem?
Yes, sir, I got it.
Okay. Now, if I'm here, then I can now choose 6, 5, 2, 1. If I choose 6, this becomes 8, 6. This becomes 5 to 1. This becomes 14. This becomes -3 and 2 coins are chosen. Similarly, here, this becomes 8, 2. 6, 5, 1 remains. This becomes 10. Remaining is 1, 2. Then if I choose coin 2, then this is my situation. Similarly, if I choose coin 1, etc., etc. So if I choose 6, if I choose 5, I did not draw 5 here. Then if I chosen 2, then from this level again, I can break it down again and again. What is the peculiarity of this one? This -3 tells me what?
So that we have exceeded the.
Yeah, so it will go to my base condition now. If z is less than 0, I will return null and infinity. Got it?
Yes, sir.
So now similarly, recursively, it will go down and you can make out that from here, this one will return null infinity. This one will return 3 coins, 8 to eventually from 8 to coin number 1 will be chosen. And this will be the solution because after 8 and 2, if I select 5, 6 or 5, again the remaining value will become negative. So from here, I will get 3 coins as the solution. From this side, if I go down, I will get 2 coins as the solution, and so on and so forth. And finally, I will end up with how many coins? Finally, how many coins will be my solution?
2 coins.
2 coins. I will get an answer with 2 coins. So, anybody has a doubt about this? We can now prove correctness by inductive proof. We have to open up the recurrence to find out the time complexity. We'll come to the solution to the recurrence a little later. But if you open up the recurrence, do you see whether we are generating identical subproblems or not?
Yes, sir.
Because 6556, 8118, 8 to 1, 1 to 8, all of them will produce identical solutions. So I have got two options now. One is to prevent creation of identical solutions in the recurrence itself, in the recursive definition itself. Or if I cannot prevent it during the creation of the recursive definition, then I have to check it by our memoization method that we just talked about. So can anybody suggest how I will modify this recursive definition and not create identical subproblems? Just modify this one, don't write a new one.
Sir, if you are now
sir, from T
Can start from
instead of
bottom I
eliminating
to
one
form.
element.
Yeah, Alapon, you were saying you started, so you tell.
so like if we are now counting in T ith element, then there is a there must have been selection where the to T1 to Tith element are already selected in the left half of the recursion tree.
Correct.
So we have already calculated that.
Correct, correct. So what will you do?
When we are in right side of the any recursion tree and we the similar situation, we subtract the Tith to Tith element from that remaining.
Correct, correct, correct. So just to repeat, here, when we are selecting one element, Ti, when we are selecting 8, we keep all the others. We have ordered this in a particular way. This is ordered. Some order, whichever order. When we select 8, then this is the remaining is 6, 5, 2, 1. But when we select 6, we throw away 8. And we retain as the remaining elements only 5 to 1. When we select 5, we know that in some option 6 will be chosen, 8 will be chosen. So we only retain 2, 1. Similarly, when we choose 2, we only allow 1. And when we choose 1, the remaining set is null. Is this clear? Aman Kumar Singh, is it clear?
Yes, sir. Yes, sir. Yes.
Arghadeep Paul, is it clear? Arghadeep Paul, is it clear? Arunavu Sarkar, is it clear?
Yes, sir.
Good, good. So we have now reduced the problem that at generation we are not generating many identical problems that were arising. But will identical subproblems still exist? Will identical subproblems still exist? Question.
Yes.
How?
Yes, sir, it can. Sir, because by taking some coin and some other different number of coin, we can go to the same state, like 8 and 6.
But how will you detect it? How will you detect it? So tomorrow I want to hear from you all whether identical problems will still exist or not. Number one. I will give bonus marks for people who identify cases where it will exist or a proof that it will not exist. The second
So
question.
like at every
Yes.
step we have different number of coins. Like in case of first case we have 4 coins to choose from. In the next case we have 3 coins to choose from, and so on.
Right.
So at every step we have different number of coin to choose from.
Correct.
And the first, like the elements are differing, 8, 6, 5, then 2, and then 1, like the one we have selected in the first case. In the subsequent case we have to select 6, and in for the other one we have to select 5 and 2, and so on. So we'll never have identical like coins.
Are you sure?
8, 6, but for the last case 1. No.
सोचो हाँ अमन कल बताना.
Sure.
And now tell me, the size of the state space will now, after removing all this, will be how much? What will be the size of the state space? What will be the size? How many nodes will be generated in the recursion? Ishan?
So I'm not sure I understand how many nodes will be generated.
Here. Here in the recursion, how many recursive calls? You know, in Fibonacci we studied how many recursive calls will there be. So here, how many non-terminating recursive calls will there be?
So n factorial, because first we're having n calls and each n call calls n minus 1 times and each n minus 1 calls n minus 2 times. So I think it would be n factorial.
N factorial comes from permutations or combinations? You're on the right track, but n factorial comes from permutations or combinations?
So combinations. Okay.
Here you are finding a sequence of coins or a set of coins?
Yes, so in the initial part we were taking sequences instead of.
Correct. This one was sequences. You are absolutely correct. And this one will be permutations, n factorial, as you have just said. Whereas this one will be combinations. So how many combinations can there be of set of subsets of a set? 2
to the power.
2 to the power n. Very good. So with this we close for today. We will see another recursive definition tomorrow, and then we will move on. But I want all of you to tell me the answer to these 2 questions. At least this first question 1. This is very critical to find an answer to question 1. So we'll stop. Any further doubts anybody has, please go through these lectures so that tomorrow we can have very interesting discussions. And Thursday, I think we are having tutorials. So we'll have tutorials. Also, an assignment has been given to you all. Please go through the assignment. Any questions? Amatya, you can stop the recording.
Okay, sure.
Was it understandable?